filters based on order statistics. Right, so these are basically spatial filters whose response is based on ordering or ranking the values of pixels contained in the neighborhoods encompassed by the filter. We are still talking about a moving window here. Moving window, let me get up in. So we've seen a few. The median filter is one of them, where you get the 5th percentile of a ranked set. It's good for salt and pepper. You have the max filter that has the 100th, it uses the 100th percentile, which basically it substitutes the mid pixel of a window, right? The mid pixel by the maximum value of the neighborhood. It's useful for finding the brightest points or for eroding dark regions. Good for pepper noise. The same way, if you get the minimum value, substitute the mid pixel by the minimum value or the 0th percentile. It's good for salt noise and useful for finding darkest points or for eroding bright regions. Midpoint filters, randomly distributed noise. It would be applied to Gaussian or uniform noise. And that's a filter that combines order statistics with averaging. What midpoint filter is just the average between the maximum value and the minimum value on your neighborhood of your moving window. This is the result of applying a min filter, the result of applying a max filter, and the result of applying a min filter on the image that we've seen before, right? Max filter and min filter on this image. And most importantly, the adaptive median filter. That's the first of the adaptive methods that we're going to see. There are at least more 2 or 3. So you see that so far we've been talking about static statistics is a bit cacophonic, right? But it is the statistics around a single pixel. But we can also evaluate the difference between these statistics that you get around the neighborhood of a point to the statistics of the whole image. That's one adaptive method. That's adaptive median filter. What it does is it works on the statistical measures such as mean and variance. The mean is the measure of intensity in a region over which the mean is computed. The mean value around this region, and the variance measures the contrast in that region. The filter operates on the neighborhood. This is the X on the neighborhood again, right? This is a neighborhood which we call XS of X and Y. Is the neighborhood around the center point X and Y. And its response is based on the value at that point, the variance of the noise, the variance of the noise of the entire image, not only on the neighborhood, but the variance of the noise on the entire image, the local average of the filter in that neighborhood, and the local variance of this neighborhood, around this neighborhood. And the behavior of the filter, or the algorithm of this filter, is the following. If the global standard deviation of noise is 0, the filter should return simply the value of G at X and Y, at the middle. It basically doesn't do anything. If the variance is 0, the filter doesn't do anything and uses the original value of the pixel at that region. This is trivial zero noise case, right? If the variance of the noise is zero, it means that there is no noise. The resulting image is equal to the original image, and I don't need to apply any changes to that. If the local variance I'm talking the variance of the pixels intensities in the neighborhood is high, the squared variance is high relative to the squared variance of the noise in the whole image, the filter should return a value close to G at x and y. Remembering that G is the image that I'm processing, like F is the input image that suffers with noise. It's called the noise eta, that generates an image G of x and y, right? So again, if the local variance is high with respect to the total variance, the filter should return a value closer to the resulting image. A high local variance, because a high local variance typically is associated with edges. So we don't want to filter out edges. We want to preserve them. So you just leave the value of the intensity as it is. If the two variances are equal or very close to each other, we want to filter the return to return the arithmetic mean value of the pixels in x and y in the neighborhood. This condition occurs when the local area has the same properties as the overall image, and local noise is to be reduced by averaging, right? So if the local area, the window, has similar statistics to the whole image, then you average it. So you have three cases. That's why it's adaptative, because it's going to adapt given a relation between the local statistics of your moving window with respect to the total global statistics of the image. That is the expression that represents formally this procedure here that we just explained. So adaptative medium filter, the only quantity that needs to be known a priori is the global variance, the variance of the noise. And this can be estimated from sampling the image. That's the stuff that we've seen in the previous slide, previous video, if I'm not mistaken. The other parameters can be computed from pixels in the neighborhood. And that's all what I need for your first adaptative filter. Very easy, very simple, easily implementable, and it gets a little bit more complex when we start talking about adaptative filtering based on histograms. That's an example of an image corrupted by salt and pepper noise. Quite a lot of salt and pepper noise, 25% of salt and 25% of pepper. This is the resulting image using a medium filter of size 7 by 7, meaning that I get a neighborhood of 7 by 7. This is something like this, 7 by 7. And this is the result of adaptative filtering, adaptative medium filtering with also a neighborhood of 7. So you can see that the adaptative filtering preserved the high frequencies, right? Preserved the edges. Whereas in the medium filter, it just got rid of it. Look at this, look at this. We lost important information here because the medium filter doesn't care about the local statistics, how the local statistics is related to the global statistics. Whereas in regions of pure noise, you can see that they both were quite good. But in regions where there is noise and some information that should be preserved, like here, you see that the adaptative filter besides of filtering the noise, also preserved the edges. That's what you want with one adaptive method. So up to now, what we've seen is we only talked about restoration in the presence of noise, right? What we've been dealing with a process that is, given your original image, you had a portion of noise that's additive noise that resulted into the image that you are analyzing. We didn't take into account degradation. Remember that degradation is an operator, is assumed as an operator that's used to that's convolved with your input image, resulting in your image G. We're going to see a little bit of that in the next video. I'll see you soon.